Oh, hello everyone. Welcome to this parallel session. Parallel session GB6 about unusual and special GRBs. We have several invited speakers and also several contributed talks. I think it's time to get started. Most of you are very familiar with each other, so let's get started with the first talk by Peter Verras on Fermi GBM and Swift BAT detection on the Magnetar jam flares. So Peter, please.
Okay, thanks, Bin. Let me start sharing. Right, so can you see it?
Yeah, we can hear you and see your screen clearly. Go ahead.
All right. Thank you. Thanks, Bin. So yeah, my name is Peter Verras, and I'm going to talk about the detection of an extragalactic magnetar giant flare. This discovery was made by Fermi Gamma Ray Burst Monitor and Swift BAT, and all the details, I'm speaking on behalf of a larger collaboration here, and all the details can be found in this paper that I cite here, and there's a link as well. Hope you can see my cursor because I want to point at stuff. Right, so I may be preaching to the choir here, but let me just say that this is Fermi GBM, which is the most prolific GRB detector flying today, has two sets of detectors, 12 sodium iodides for low energy gamma rays, placed in groups of 3 at the 4 corners of the spacecraft, and for higher energy gamma rays, 2 BGO detectors placed on the opposite sides of the spacecraft. And so this diagram here shows you how Fermi observes the entire unocculted sky. And the little gray circles running around are the detector normals. That's where the detectors look. So this animation is courtesy of Adam Goldstein. Is captures a fraction of the Fermi's orbit, and I forgot to say the blue circle is the Earth. So that part of the sky is occulted for Fermi. Another important bit of information is that the temporal resolution is 2 microseconds for Fermi. And this analysis that I'm presenting was also using Swift BAT data. So Swift BAT didn't trigger on this event, but there's a new pipeline called Guano that retains the high resolution data from external notices that otherwise would be thrown away if there's no BAT trigger at that time. Okay, so still at background, these are Magnetar giant flares on this slide. There are 3 actual gold-plated giant flares that we know of. And the main characteristics of Magnetar giant flares are the short spike at the beginning, very, very, very fast rise, very bright, and notice here the log scale for these bottom 2 plots. And the short spike is followed by this modulated oscillating tail, which is much dimmer than that. So it's been long suspected that these giant flares can be masquerading as short GRBs, because if you place them at large distances, I should mention that these 3 were observed in the local galactic neighborhood, 2 in the Milky Way and 1 in the Large Magellanic Cloud. So if you place these objects a bit further away, you wouldn't be able to see the oscillating tail, only the bright pulse. And the characteristics of that bright pulse is the bright pulse are very similar to short GRBs. I should also note that both of these 3 events were so bright that the detectors that observed them were typically saturated, so they couldn't make proper observations. Okay. And before I jump into my part of the talk, so Fermi GBM's role in these observations, I want to advertise the other works that have been done on this event. So this event is GRB 200415A. We refer to it as a GRB, and but but you could think of it as a Magnetar giant flare. So the first paper is by the Conus Wind team, and it concerns the localization using triangulation techniques. You can see this plot here. They nicely localized it using different instruments flying around in the solar system and detecting this event. So they nicely localized it to the Sculpture galaxy, which is about 3.5 megaparsecs away. The other interesting bit about this event is that it had, for the first time in MGFs, for Magnetar giant flares, had GeV detections. So Fermilab detected GeV photons from this event, and you can see the localization region for Fermilab. So it detected three photons, but these 3 photons are confidently associated with this event. And the third paper concerns the statistical characterization and uncovering new Magnetar giant flares. And you can see that some candidates here, and Eric Burns is leading this effort, and stay tuned for his talk coming up after mine, I think. Right, so all in all, we could say that this event that we call a GRB is a Magnetar giant flare. Okay, so when I was thinking how to tell the story of this event, this burst or Magnetar giant flare, I was reminded of this children's book called Flotsam, and so the story goes that this blonde boy here goes to the beach and finds a camera. And the camera has a film, and he develops the film, and the film contains many magical photos. But one of the most interesting one is a photo of a girl holding a picture of a boy, and the boy is holding a picture of a girl, and so on, out to like 10 levels. So back to the beginning of the 20th century. So that reminded me how to present this event. So we can go from very large timescales down to very short timescales. So it triggered Fermi on 8:48 UTC, and so you can see here the first. These are the light curves that we usually look at for any gamma ray trigger. So the first top figure shows just one bin of exceedingly bright excess above an otherwise usual background. If we zoom in, so the middle plot shows about 1 minute with 1 second resolution is still just one bin, no structure. And if we go to 256, it's a quarter second resolution, it's only one bin still. So the green light curve, we have to go to 64 milliseconds to get to start to get some structure here in the red curve. Okay, so it's just the first impression. So it's very bright and very short. Okay, so if we analyze it and in the context of short GRBs, it turns out that it's quite extreme. So the peak flux is 98th percentile, the photon index is very hard, 89th percentile, the peak energy is high, 79th percentile. So these all kind of hint at a non-GRB origin, so it kind of sticks out of the short GRB population. Okay, so let's zoom in one more level. So you saw the 64 millisecond light curve, but we can still zoom in. And this is where Swift Guano comes in. And using this, using Swift Guano data, we were able to get the duration of the event, which turns out to be about 0.14 seconds. So we chose Swift Guano because it didn't have the data problems that GBM had for short slices of the event. We searched also for pulsations that we didn't find, but we weren't discouraged by that because at the distance of Sculpture, we weren't expecting to find any pulsations that were similar to previous Magnetar giant flare pulsations, and also no radio detections for this source. Okay. And now we're zooming in some more, okay? And So let me just walk you through this picture, this figure. So we had the T90 figure here. So that's T90 consisted of a pulse and some kind of a shoulder going down, and we're zooming into the pulse here. So the width of this figure of this plot is about 25 milliseconds, and the resolution is 0.2 milliseconds. And for reasons that will become obvious in the next slide, we colored the light curve into 4 colors. So we chopped up the light curve into 4 intervals. And on this plot, I just want to show the data problems we had. So this is the first kind of data problem when we were saturated. The top light curve is from Fermi GBM VGO detector, the higher energy detectors. These are the lower energy detectors of Fermi GBM. And the bottom light curve is Swift-Path, sorry about that, Swift-Path light curve. So you can see here the light curve is sort of flat. That is where Fermi GBM was saturated. And we correct for the saturation using the Swift data. So we fit spectrum to both Swift and Fermi GBM in the Swift energy range, and we correct the Fermi data for that. And here you can see some holes in our data, and so that's at the end of one data packet and the start of another one, and apparently we lost some photons there. So we correct for this by just fitting a function, fitting the decay of this light curve. That's not a big issue here. Okay, and so this is our main result here. I should say one of our main results, and we can zoom in even furthermore. So this plot was the light curve here, and I am showing you a zoomed in portion of the first pulse of the first slice here. So if you take a look at these red part, that is zoomed in here, and the resolution now is 12 microseconds. So the one of our interesting find is that the very first pulse had a very short rise time. So the rise time here, we fit this initial pulse with the pulse model, I should say, and we find that the rise time is 77 microseconds. That's really short. That sticks out in terms of Gamma-ray burst rise times or variability times, and also Magnetar giant flare rise time. So that's the shortest time scale we found for GRBs or Magnetar giant flares. Okay, so these are the intervals, the 1 through 4. So the first, as I said, was the fastest. The second, we chose it because it was the brightest one. So the peak isotropic luminosity here is about 10 to the 48. So this is the second interval, and you can see the spectra of these intervals in the same color code. So this is the orange spectrum. The third interval turns out to be the hardest one. So the peak energy of the third interval is close to 2 MeV. So that's the blue spectrum here. And the fourth interval is not special in any particular way. It just covers the rest of the photons up to the end of the T90 period. Okay, so I'm showing a lot of numbers here. I just circled the interesting ones that I mentioned. And if you have any questions about them, just feel free to ask later. Okay. Next slide. We did fit the time-dependent spectrum. We found that at all times the spectrum was best fit by this power law with exponential cutoff model, which is shown here. Oops. And what was interesting, we found that we can model the flux as a decaying exponential in time. So you can see that on this plot with the time constant of 45 milliseconds, and also the EP could be modeled with the same decaying exponential with a time constant of 100 milliseconds. Another interesting thing in the bottom plot, the flux correlates with E peak, and it goes as E peak squared. And I mentioned we looked for QPOs, quasi-periodic oscillations, but we didn't find any except this 180 hertz, which we didn't want to claim as anything significant. The chance probability was too high. It was about a 2.5 sigma result. We also looked for the highest energy photon, and we found we found that we could ambiguously claim 3 MeV photons. So those are securely associated with the event. We have some 9 MeV photons, but we couldn't unambiguously claim that those belong to the event. So on this plot, you can see the black dots are actual photons. So the y-axis is energy in MeVs, and the x-axis is time. So the blue box shows you photons from 2 to 3 MeV, and the red box shows you photons from 4 to 10 MeV. So we could prove that these photons are above the background, and these are also above the background, but not significantly. So the main point here is that we found 3 MeV photons originate from this giant flare, and using that very conservatively, we could put a lower limit on the Lorentz factor based on pair creation arguments. So the Lorentz factor has to be at least 6, which proves also for the first time that this Magnetar giant flare is relativistic. Okay, so a little bit about the interpretation. So it is relativistic of at least 6, a Lorentz factor of 6, but based on dynamical modeling, we could say that it has to be closer to 100. The spectrum is very narrow, but still non-thermal shape, and we argued that Comptonization is the process that shapes the spectrum, and being that it's very close, the spectral index, the photon index is very close to being flat, that disfavors the synchrotron origin for the spectrum. For the time evolving spectrum, we have these decay time scale for the flux, or the luminosity, as it goes as e to the minus t over 45 milliseconds. So these 45 milliseconds could be interpreted as this rotating beam passing our line of sight. And if we just assume some fiducial period for the Magnetar, like 8 seconds, and some reasonable Lorentz factor, we could recover this 45 millisecond. And for the flux goes as E peak squared relation, we interpret that as a simple relation between them based on the Lorentz factor. So the flux goes as luminosity and is a function of, goes as Lorentz factor squared, and E peak goes as Lorentz factor to the first power. And if there's and if you can neglect everything else that these quantities depend upon, you can just simply relate the two and recover the relationship F goes as E peak squared. Okay, I forgot to start the animation, but it just it's a nice animation, and I think I'm getting close to my my time. So in conclusion, I just presented to you the first Magnetar giant flare that could be analyzed in detail for the and is just hope I convinced you that 200415A was in fact a Magnetar giant flare, and there it had record-breaking properties like the short time scale, the 77 microseconds, and the highest photon energy, or the first definite proof of relativistic motion. And as I said, the details are here in this paper, and I put a link to it as well. Thank you for your attention.
Thank you, Peter. Any comments or questions for Peter? You can just unmute yourself and ask questions if you have anyone.
Yeah, I have a question. Peter, you mentioned it's the first one we could do detailed studies of. Was there some observation missing or some key piece of information you would have loved to have? Maybe the QPO or something?
Yeah, the QPO would definitely be the smoking gun. I guess the QPO is the only thing that otherwise we have it covered really well.
What about radiation mechanisms? You mentioned that it's definitely not single chunk, but what about other physical process? Do you model this in first principle and compare?
We just model it based on simplistic formulae.
Oh.
So yeah. But that could be a good project.
Yeah. Okay. Interesting. It's a missing data problem. Is that always happening in the data? So it's actually when I saw the gap, a little bit weird to me.
I don't think we've encountered this before. So this is, or at least not to my knowledge.
Okay, is it like the plant of, the satellite problem or data package or something?
I mean, it's not hard to identify. So if it happens somewhere, we would see it, I guess.
Okay, thank you, Peter. I think we should move to next speaker, Eric. Eric will talk about Magnetar Gen flares as a progenitor of short GRBs in general. Okay, go ahead, Eric.
Okay, thank you, Bin, and happy to be here to talk about this paper. This was, as Peter mentioned, one of four that we coordinated that took us a bit of time to get out, but the citations on the bottom, and I'm presenting on behalf of many authors who made some critical contributions. So just, I'm going to go a little bit more into the background than Peter on gamma ray bursts, because I kind of want to show why we were motivated to do this study and maybe what we could learn from it. So we've seen cosmological GRBs for 50 years. We've seen a lot of them. They're from kind of the nearby universe, at least in extragalactic terms, and sometimes hold the record for the furthest events ever detected or seen. Two classes, short and long, based on duration, which goes from maybe 1/100th of a second up to 10,000 seconds in the most extreme cases. And these are the most luminous electromagnetic events since the Big Bang. So almost all of these, or all of the cosmological ones, are powered by cataclysmic events. So long gamma ray bursts come from a rare type of core collapse supernovae called collapsars. You have a very fast rotating star that undergoes core collapse, and that fast rotation allows it to have really incredible accretion rates, which powers the ultra-relativistic jets, which propagate outwards and release the gamma ray burst. And this we know because we've seen now a few dozen long gamma ray bursts, which a few weeks later are followed by the relativistic supernova signature. And the other kind of smoking gun proof of a gamma ray burst progenitor comes from LIGO in 2017. And they kind of proved something we expected based on more than a decade of observations from Swift. But they gave us the first direct detection, shown on the left, of a low mass compact object in spiral, which was followed about 2 seconds later by a gamma ray burst detected by Fermi GBM and integral SPACS. And all of that together gave us that really the proof that neutron star mergers power most short gamma ray bursts. So that kind of brings us to the main topic, which are magnetar giant flares. And this is an image that the light curve on the left that Peter showed from the first detection of a giant flare, where you have this really short duration. Main peak, it's maybe up to 100 milliseconds long. And that's caused by a star quake, which releases kind of the outflow that Peter's animation showed. And then you get this hotspot on the surface, which following the rotation period of the star gives you this periodic oscillating tail that decays as it cools. And this was how we first saw magnetars, and these emission mechanisms are how we understood really what they are. And they have these enormous magnetic fields, and now there's about 30 of them known. And as Peter showed, this periodic tail is the smoking gun signature, which we see for the galactic events. But when you get beyond about a megaparsec or so, all of that tail emission kind of fades into the background and becomes undetectable with current instruments. But the main peak survives. And it is very bright, so that would look like basically a standard short GRB in our data. From 3 events in the Milky Way over the past 50 years, you can get one every few decades for Milky Way-like galaxy, and there are, say, 100 of those in the quite local universe. So these have to exist in our data, and people have discussed this for the better part of 20 years now. Peter also mentioned that these events are better to study, at least for the main peak, because you can get unsaturated observations without detector issues. So without the smoking gun signature, the way that they have to be identified is through spatial alignment with known galaxies. So our paper came out almost a year after that gamma ray burst occurred, the one that Peter talked about that kicked this work off. And we were not the first to compare it to the larger short gamma ray burst population. So I wanted to focus really on what I think was our key contribution to understanding this event. So we constructed 2 really large catalogs, and the first one was a short GRB catalog. So we cut on the kind of usual threshold of 2 seconds. We needed a measurement of the bolometric fluence, the total energy output. They had to be reasonably well localized, at least for us, to about less than 4 square degrees. And we removed bursts with redshift, placing them far into the universe where we could not detect giant flares. And we combined data from many missions, so BAT CNC-GRO, Swift-BAT, Fermi GBM, CONUS Wind, and it looks like I accidentally left off integral SPACS, which was also very important. And then we also combined all of that with the interplanetary network. So these are detections of the same events by multiple spacecraft using the finite speed of light to draw a timing annuli in the sky and give really nice localizations on the sky. And in the end, after all of those cuts, we ended up with 250 short GRBs that met our criteria. The other catalog was our galaxy catalog. We needed the position, so including the distance, the size on the sky, the angular size represented as an ellipse, if it was available, the measured star formation rate, and considered events just a little bit beyond the Milky Way and at satellite galaxies and out to far beyond where we can detect at least the galactic giant flares that we've seen. Really the 2 key catalogs were the top 2, the Z=0 multi-wavelength galaxy synthesis catalog that tries to provide really nice measurements of star formation rate, stellar mass, specific star formation rate for nearby galaxies that do have large size on the sky. And the second key one was the census of the local universe catalog built for gravitational wave, EM follow-up of gravitational wave detected neutron star mergers. We added the local volume catalog and some additional information from the NASA extragalactic database in Hyperleda, and ended up with about 130,000 galaxies. And what we did was we compared the short gamma ray burst localizations against the positions of these galaxies. And this is really the most technical part of the paper. So if you want full understanding, then maybe bug me later or check the paper. But In brief, it comes down to two PDFs on the sky. So PGRB is just the gamma ray burst localization. PMGF is a little more complicated. So it's the probability that a given position is to have produced a giant flare with a fluence that we observed at Earth for a given event. And the way we do that is we take our galaxy catalog, we place all of them on the sky, including their angular size. We weight them linearly with the star formation rate. So giant flares come from magnetars. Magnetars are only active for something like 10,000 years. We're pretty sure they come from core collapse supernovae, and core collapse supernovae track the star formation rate. So it should be, SFR should be a pretty good proxy for the rate of these events. The second weighting for each position for a given galaxy was building an assumed energetics distribution. So a power law, just like most magnetar outbursts behave or follow, where the lower energy ones are more common than the higher energy ones, and then we can take the distance to that galaxy against the fluence observed at Earth, determine the EI, so if it came from that galaxy, and weight it according to that, where it falls in that distribution. So that's a little complicated, but the formula at the end is nice and simple there at the bottom. Omega is the likelihood that a given gamma ray burst has a giant flare origin. So it's 4 pi times the sum of multiplying those two PDFs divided by the area of each pixel. And all of this was done in HEOPIX. And we found 4 gamma ray bursts that come from the local universe. The left two have been discussed in the literature before, 05, 11, 03, and 07, 02, 01, which the IPN teams years ago identified as likely coming from M81 group and Andromeda, respectively. On the far right is the one Peter introduced from last year, 2004-15A, which is alone the most significant, about 1 in a quarter million chance alignment. But we ended up finding a 4th one, which is 070222, localized to M83, and a special thanks to the IPN guys and the integral team, who, when we found this as kind of a marginal candidate with a single, the narrow annulus going up and down there, and integral found an additional detection of the event, which allowed us to cut out that quadrilateral and really place it at M83. And this event is pretty interesting because it actually has 2 distinct pulses. So either, as Peter showed, that kind of plasma outflow, either 2 of those were released from the same starquake, or there were 2 starquakes in really quick succession releasing different outflows. But we're still kind of trying to figure out how that happened. So from simulations, we can calculate with 250 short GRBs how often we get 4 of them this significant, and that's shown on the right with a cumulative plot of omega. In blue are the 1, 3, and 5 sigma confidence intervals. So at both 3 and 4 events, we hit discovery significance. So this is, we're absolutely certain we have identified 4 local GRBs. The closest one by a factor of nearly 1,000 in volume. And the known progenitors are excluded. So they are too short to be collapsars, and there's no supernovae noted in optical surveys. And additionally, there's LIGO non-detections for 3 of the 4, saying that they cannot be due to neutron star mergers. So we checked if they're consistent with giant flares, which again, we expect in our data. And we checked 2 key parameters. So on the left is a measurement of the rise time. In orange is our sample of these 4, and in gray are the close values for the galactic MGFs, and then in blue are the wider short GRB sample. So these have much faster rise times, and then on the right, much lower total energies than cosmological short GRBs. And each of these is independently about 1 in 1,000 chance, by calculation by chance. So we're we're almost certain or effectively certain that these are giant flares. And then with that, we can kind of learn more about giant flares or potentially even magnetars. So this is a calculation. If you have a given number of MGFs and you account for your sample completeness, you divide it by your observed space-time volume. There's a scaling factor for the local overdensity of galaxies and star formation rate. And you end up with a scaling factor that you can apply to the image on the lower left, and end up with, you just marginalize it out and you end up with an inferred rate for magnetar giant flares. And that comes out to 3.8 times 10 to the 5 parsec cube per year, which is a really enormous rate, 1,000 times higher than other gamma ray burst progenitors. And that lets you, a little bit of a typo here. So this is our sub-event times F lower M. So the rate of giant flares you can relate to the rate of their events that could form them times the fraction of those events that actually do form them, times how long magnetars are active, and then the rate of giant flares per magnetar. These last two we have a reasonable understanding of, or we can at least place very conservative constraints on them. But even with those, we get two nice results. And the first one is that the rates of giant flares are so high that their progenitors or their formation rates also has to be very high. And that rules out a large number of possibilities. When you combine that with the host galaxies, which have high star formation rates, but also have high metallicities, then those two together favor normal core collapse supernovae as the dominant magnetar formation channel. And additionally, the rates are so high that some magnetars must produce multiple giant flares. Neither of these are really surprising. I think this is generally what people expected, but it's nice to really have some additional observational proof of that belief. So just one quick look to the future. The upper left is the three kind of what we call galactic giant flares, which you could have detected with the first generation of GRB monitors. The lower left is expanding out to the four that I described, including the event from last year, which really required the more modern GRB monitors like Fermi and Swift. But if we want to get more of these, we need to go even bigger, more sensitive. So I'll just briefly highlight Starburst, which was selected for a non-competitive phase A, which means if we stay on budget and stay on time, we get to go forward to a launch in the mid-2020s. And potentially these events are sources of gravitational waves and fast radio bursts. A lot of uncertainty and lack of knowledge there, but it'll be nice to explore them in partnership, LIGO Virgo, and of course the FRB community. So here's my summary slide. So I think we've shown really the third known GRB progenitor. The first one's at repeat. We also did the lat detection of GeV emission, and we found one with two pulses, which is, I think both of those things are quite surprising and really hopefully things that we can figure out in the next few years, either with advances in theory or, ideally more detections. So I'll stop here and thank you for your time, and I'm happy to take any questions.
Okay. Anybody have any questions from the audience? Let's go ahead to unmute yourself.
Here's Thomas. When you show the pictures of the galaxies and like the IPN localizations, I was just wondering if you have any sense of the offset that you would expect for those magnetars, because some of them, I was just curious about the first one actually, because it looks like kind of far from the galaxy.
Yeah, it's, I think I can this might be, they can stop sharing. Let me reshare. Yeah, it's a really good question. And that was really why this was kind of an unsolved thing for, or kind of a you can clearly see it does not directly align with either M81 or If you dig into a paper from OFAC in 2005, you look at the GALAX data. In that region in between, there are UV knots tied to what they believe is high rates of active star formation in those specific regions. And that's tied to the fact that M81 and M82 are interacting galaxies. And that was a likely explanation, still a bit debated. Interestingly, this potential nearby FRB that was discussed is maybe coming from M81. Kind of, it's not the same location. It's up to the right of it, I believe. But it's the same case of maybe the interaction between the galaxies. So all of that together, I think, makes sense to me. But definitely that one is a little bit, surprising, I think.
Yeah, thank you.
Yeah, interesting. Of the four bursts, I think two of them are previously started, right? The two new one is 07 burst. In my estimation.
Yeah, exactly. The left two, the IPN guys discussed for a while. The right one was from last year, and then through this work and basically because of all the data people have saved and worked together for decades at this point, we really got to get the fourth one. I think there's more in Fermi GBM data, but it's going to be pretty hard to identify them without the IPN localizations.
Yeah, exactly. Okay, interesting. Okay, any other questions for Eric? If not, we should go ahead with next speaker, Jun Yang, who is here, and he'll be talking about the GRB 200415A. So go ahead.
Hello, Mr. Chairman and honorable guests. I'm Jun Yang from Nanjing University in China. It's great pleasure for me to be invited to give this talk. My title is Magnetar Gender Field Origin of Gamma Burst. They are my characters. In this talk, I am going to show our recent work about unusual GRB 200415A. Actually, with the joint detection of the gravitational event GW 170817 and the short gamma burst GRB 170817A, the important issue in GRB field about the classification and the physical progenitor had a great breakthrough. Here we first go back through the traditional classification picture before we discuss other origins of GRB. Traditionally, the main classification scheme is long-soft GRB versus short-half GRBs based on the T19 duration distribution and hardness information. However, in this classification scheme, the boundary between two clusters is not very clear. For example, in the right two fix, the duration distribution is detector dependent and energy dependent. Compared bio scheme, the physical classification is more meaningful. Now we have known that there are two channels to produce GRBs. Type 1 is related to compact star modes, and type 2 is related to the dense massive stars. As the understanding of the connections between observations and physical physical nature depends, we can use more observational information to classify GRBs, not only duration and hardness, but also the supernova association, star formation rate, and offset, and also some empirical correlations like anti-relation. But there are still some unusual GRBs being outside this frame. One of them is GRB 200415A. About this event, also see talks by virus and bones. So why is it unusual? That's because it's a short GRB, but does not originate from a compact star module. The direct hint is its localization. In the left figure, the black arrow box is IP localization to this processor. And the purple cycle is Sculptor Galaxy, also named NCT253. Their change probability is very small, means that NCT253 is the host galaxy of this processor. And this galaxy is a starburst galaxy. Means inside it's undergoing intense star formation. Then here comes the first unusual thing. That's because most short GRB host galaxy is early type with little star formation. Here, the observational properties of GRB 200415A are listed in this table. We can see that its short spec is very short, but its peak energy is very high. And its astropic energy is very small, like GRB 170817A. So it should be an off-axis GRB if we think it originates from a compact star module. Then there comes the second unusual thing. As an off-axis GRB, can it have such short duration and high peak energy simultaneously? We think it's difficult. Firstly, for the simple top-hat model, if we assume a typical on-axis astropic energy, then we'll get extreme small on-axis duration and extreme high on-axis peak energy. Such extreme values have never been observed in GRB samples. Then for more realistic structural digital model, even we have not detailed calculations here, but we can meet that its peak energy profile must be quite flat, but its energy profile must be quite steep. Such conditions are at odds with most studies of GRBs. In addition, GRB 170817A can be explained by off-axis structured jet model, but in comparison, GRB 200415A has similar astropic energy, but such small duration and much small duration and much larger peak energy. And GRB 200415A is close to us, but we did not detect kilonova and afterglow. So we think that GRB 200415A is does not originate from a compact star module. The EP versus ESO correlation diagram gives us a direct presentation. It's clear that GRB20 is a significant outlier away from the short GRB track. If we want to it look like a type short GRB, we need to put it in at least 40 times for the distance. But interestingly, this process is very close to the Gen flare. Implies that the Gen flares may be another population of GRB. In the past, there are only 3 confirmed Gen flares from SCRs. Up to this day, we all know that SCR is young magnetar with extreme high magnetic field. So the question is how GRBs can originate from magnetic Gen flares. The left figure shows the light curves of a nearby Gen flare. It's so close to us, so we can clearly see its sharp initial pulse and weak pulse intervals. But if a Gen flare is from a magnetar in distant galaxy, its pulse interval will be buried in noise, but its initial pulse can still be detected in the form of a short GRB. This point had been proposed in some papers and previous talks by Veras and Bones. In previous samples, only several short GRB were considered to be candidates for magnetic Gen flares. The main argument is that they come from actual galactic galaxies and they have similar astronomic energy to Gen flares, but there is no as much evidence as GRB2415A. Here we list the spatial and temporal spectral features, origin and track mechanism of Gen flares. Next step, let's check the consistency between GRB2415A and Gen flares. Firstly, in this table, the consistency on spectral features and energy is very clear, and they are all located in clusters and galaxies with high star formation rate. But GRB2415A is much further from us. That's why we did not observe its pulse interval. This slide shows the consistency on temporal features. The left figure shows the light curves of GRB2415A, and the right figure shows the initial pulse of a Gen flare. We can see that they both consist of an abrupt rise and exponential decay. And due to the no detection of pulse intervals of GRB2415A, we are not clear about the corresponding features like period and cupules and possible cupules. In order to check the consistency on spectral features, we performed refined spectral analysis. The best model is determined according to the Bayesian information criteria. We found that the multicolored black body is the best model during sharp spike, and the black body model can best fit the most spectral during decay phase. So The energy spectra of this burst include some significant thermal components, which is consistent with jet flares. It's also clear that its spectra are totally hard and rapidly evolve like jet flares. This slide shows the consistency on emission region. In the upper left figure, we notice that it has one of the smallest minimal time variability among all GRBs. This implies that its emission region should be small. And the lower left figure shows the spectral length of this burst. We can see that all of the lag values are very tiny. Such feature is consistent with one-time field-like emission region. The right figure shows the spectral evolution. Some parameters like peak energy and temperature show significant intensity tracking pattern evolution, which usually implies the thermal emission region. Lastly, this slide shows the consistency on EP versus ES correlation diagram. It's clear that there is a new track on GRB200415A and jet flares and their candidates. Based on above consistency, we made this table to show that jet flare is a natural solution to produce GRB200415A. We also noticed that the properties of GRB200415A are not unique. There should be more additional cases to be found, and to identify GRB candidates. The similarities on temporal and spectral features and possible QPUs may be important clues. The jet flare already makes GRB formally connect to stable magnetars. And interestingly, the SCR both seem to share the same track with jet flares, and FRB can be associated with SCR both. These connections may bring us more surprise in the future. Lastly, I will skip my summary. That's all my talk. Thank you for listening.
Okay, thank you, Yun, for the talk. Any questions for the speaker? Yes, please, Rod. Go ahead.
So the measured isotropic equivalent energy is large, 10 to 46. So can you discuss the possibility that the outflow is collimated or not?
You mean the jet?
Right.
Yeah. If you can show the table showing the isotropic energies compared with other gen flares. Our point is consistent with gen flares, but if you think this is GRB, it's hard. Yeah, kind of hard to. It's not hard to produce this energy. The problem is the very sharp spike and very short durations. You have to assume either it can be a uniform jet or a structured jet. And in both cases, we have some problems, like you either have a very high energy, then you see the low energy effects, or very different structured jet structures, then you can see still see a very sharp spike with a relatively high energy. So this is kind of unnatural, but on the other hand, you will assume this is Gen flare. These energies are consistent with any other Gen flares. So I think maybe, I'm not sure whether this can answer your question.
Okay.
Yeah. Oh, Thomas, go ahead, please.
Oh, I was just wondering because all of this sounds very tricky using only GRB gamma ray data. So I was wondering if you would expect any emissions in other wavelengths to, confirm the origin.
Yeah, unfortunately, no. I mean, the smoking gun will be definitely the QPOs. But Fermi paper has a QPO measurement, but eventually the signal to noise is too low, so cannot claim that. I think the most promising evidence is the location. So location is consistent with nearby galaxy, and we have something similar to Gen flare. You will assume it is related. I think that's the most evidence. I'm not sure whether Eric or Peter is still here, but I think that's the main point. We assume it is there, then it is. I think Yangjun also gave another, in the second last slides, you show the additional cases. You didn't mention in slides 18. Go to slides 18, this one, yeah. Slides 18, yeah, this one. You can see there, actually, we did see a QPO in the bottom right. When you see the blue one is another burst. You can scale the blue one to this burst, which is the red one. The two are very similar. And interestingly, the blue one is much stronger, and we found a QPO on this burst. The QPO is much more significant than the 200415A. However, there's no host. It kind of, yeah, interesting, but still we need some host. I mean, you can search, you can either try to search deep and try to identify some hosts, but maybe the host is too far, is too faint, you cannot detect anything eventually. But in this case, the QPO may be a very strong tool to identify those kind of Gen flare GRBs. Okay, any other questions from the audience? Okay. Oh, if not, I think according to the program, we should have a break. What time is it now? Let's come back on 18 minutes, which is 1:15 in Beijing time. Maybe it's different in your time zone, but we should come back in 18 minutes. Okay. Hello, Bruce, you want to share your screen? Okay. Yeah, we cannot hear you actually.
Yeah. I'm just
Okay.
repeating everything.
Yeah, everything good. Welcome everyone to the second half of this parallel session. Our first speaker now is Bruce. And we'll be talking about ultra-long GRB's current and future prospect. Okay, Bruce, go ahead.
Yeah, thank you. So yeah, basically the talk is a bit different because I'm not speaking about any peculiar event, but rather about the class. I was not able to fit all the title into that slide, so that's the reason why I just call it ultra-long gamma ray bursts. But I'm supposed to bring you the current and also how the thing will evolve during the next few years, hopefully. So just to put some kind of context, I went last week to basically dig out this figure, which is the very start of the classification of gamma ray burst by durations. And so far we are focused on this part. You have there the boring normal long gamma ray bursts. I don't think this is the correct session to discuss about that. And personally, just to put you in fix, I will focus on what is here, bursts that are not even on that figure. So the initial fact about ultra-long gamma ray burst is that it emerged during the year 2000, 2010s, that several bursts have a continuous emission for more than 1,000 seconds. The first hint came with BATC, but the problem with BATC is that because of the location and the fact that the Earth was passing inside the field of view, it was difficult to really state if you were seeing the same burst that was lasting very long, or you were seeing 4 bursts that were more or less at the same position. It's continuous wind that the first one really told you that there is something there which is interesting. But problem with continuous wind is that still it's difficult to make a follow-up of these events. And in fact, most of the bursts that I will discuss now are detected by Swift. This is just a selection effect, but it's important to understand it. The second point, which is problematic, is that it's not very easy to classify a burst as long or ultra-long gamma ray burst due to the way that we are classifying them by the duration. The problem is that the duration is highly dependent on the instrument. You have the absorption band, you have the sensitivity of the instrument, you have a dialectic cycle. If the Earth is passing inside the field of view, for instance, it's very easy to stop the observation. And then if you cannot basically confirm that is the same position, the same source that you see after the Earth has passed away, the field of view, then it's basically difficult to make the exact computation of the duration. And because of that, Bing Zhang in 2009 with some collaborators have proposed a method to remove this observational bias, with basically based on the duration, the shape of the light curves, the supernova associations, the redshift, the spectral hardness ratio, you have also here I'm reading the circumburst medium kind. Problem being that at the end you have indeed something that will classify very precisely the kind of burst, but in practice, when you are facing with the observations, it's very complicated and not very practical if you need to make an early guess of what you are seeing. So that's the reason why at the end, when we handled with Julia Strata at start the problem of the classification of long and ultra-long gamma ray bursts, we needed to go into a band where there was no instrumental bias, and we choose the X-ray band. And thus, that explains why at the end, most of the ultra-long gamma ray bursts are classified by Swift, because there we have the X-ray observations. So if we take this, the canonical Swift light curve, which you have on that figure, is defined by several segments, and the segments 0 and 1 are explained by the prompt emission. The transition point, so between 0 and 1, which correspond to that thing, is the point when the central engine stops. So technically, that's the end of the prompt phase, as explained by the physics this time. So this is the best estimate of the physical duration of the event. And we define that as Tx, the duration of the central engine activity. So with that, it was possible to go inside the Swift catalogs and basically to classify the event between long and ultra-long gamma ray bursts. That bring us to the possibility to offer a third class of gamma ray bursts. So Peter and Eric earlier have explained to you that you have a class of long soft gamma ray bursts that were detected in 1973. Then the short hard gamma ray burst detected in '93 by Krista Covello, and basically we were able with Julia and Michel Bauer in 2013 to add to that thing the class of ultra long and energetic gamma ray burst. I bring your attention already, students, to something important. It's every 20 years, so start preparing yourself for 33. Something could be interesting there. And basically during the first year, we had an issue in the sense that it's difficult to do statistics on one or two events. And at start, you had the discussions about the ultra long class by itself. Is it the tail of the distribution of a long event, or is it a new class? So the only thing that we had to do there was to wait in order to have enough statistics into the distributions to prove that at the end, the ultra long gamma ray bursts are not compatible with the distribution of a tail of normal long gamma ray bursts. So once we have proved that we have indeed these three classes, we were able to start thinking about the way to make a kind of definitions. There it's a bit complicated because at the end, the only way that we have to make that classification is on the duration of TX, the value. And we basically have there to rely on distributions. So we were able to state that at least 5 of these events, 10, 12, 25, 11, 12, 09, 12, 10, 27, 13, 09, 25, and 17, 07, 14 were indeed ultra long gamma ray bursts. This one, there is no doubt. We call that the gold sample. They're lasting all more than 5,000 seconds, and they are not compatible with the tail of distribution of long gamma ray bursts at more than 3 sigma. And then we have the gray area, what we call the silver events, which are not gold events. They are still lasting more than 1,000 seconds, but they are compatible. They are not compatible only at 2 sigma. So it should be possible that inside that sample of silver events, you have 1 or 2 normal long gamma ray bursts that are just the extreme tail of the distribution. It's difficult to really decide. So at the moment, we just have them there. And then from that sample, it was possible to start to study basically their properties one after the others. So if we go for a prompt, let's just kill the elephant in the room. We know that they last longer, so it's not interesting to follow that. It's basically their own definitions. But at the level of the instantaneous properties, we can see that at the end, they have a similar spectral shape than normal long gamma ray bursts, a similar distribution of mean flux. So basically, there is no difference between long and ultra long gamma ray burst. If you just take the instantaneous observation of BAT, you cannot state if you have a long or ultra long gamma ray burst. Now, if you go into the integrated properties, so basically, if you start to integrate, they are releasing more energy in total, but with the same emission rate. In fact, if they are releasing more energy, it's just because they're lasting longer. So the difference that we do see is that it's a difference in the amount of energy produced by the central engine, but not by the emission mechanisms. So that tells you that at the end, the central engine should be more or less similar. At the level of the afterglow, if you're looking to the main properties, they have similar fluxes and spectral shape than normal long gamma ray burst. I've just put one case, 111209A, that we studied with Julia Strata. We don't see a very strong difference between the two in the afterglow. At the level of C-Cambus medium, when we are doing some kind of modelization of the light curves and the spectrum, we do see that a stellar wind is preferred compared to a constant isotropic interstellar density medium. We also know that you have supernova, which are possibly associated. They are unusual. It's not the standard 1BC supernova that you do find for normal long gamma ray bursts, but there are still some supernova. And interestingly, a last point is that we also do see in several of these objects a thermal component that do appear when the prompt phase start to phase out, so that we can see it. We mostly understand that as an interaction between the jet responsible of a burst with stellar layers due to the progenitor. The best case is 130925, but you have other examples like that. This is also something which is not specific to ultra long gamma ray bursts. Some normal long gamma ray bursts have also shown a hint of thermal components. So at the end, it's difficult there to state that any of these properties are linked to the ultra long gamma ray burst. So again, all of that tell you that you should have something that is more or less linked to the central engine and not the way that the system is working. So why we are studying ultra long gamma ray burst? At the moment, the main question is about the progenitor of these events. We don't understand exactly what kind of object could produce that. We need to provide enough energy in the time scale of the event, so something which is lasting for long, and still be a compact source, because we know that we are still dealing with compact objects. So at the end, we have three classes of progenitors that are possible. Ultramassive stellar progenitor, possibly with low metallicity. That was the initial model by Suwa and Yoka. The recent works that I've seen so far are starting to relaxing the low metallicity conditions by using periinstability inside ultramassive stars. It's still basically ongoing, but I will classify that as just the ultramassive stellar progenitor. Then you have a tidal disruption of dwarf stars by basically a black hole. So it's something which is linked to the standard tidal disruptions events. And the Magnetar formation with basically all the energy provided by the Magnetar. So as I can tell you, we have the same emission rate for both long and ultra long gamma ray bursts, the only difference being the duration and the total energy. We have the same afterglow emission, which is linked to the environment. So that means that we should have the same environment for both long and ultra long gamma ray bursts. So that would privilege a similar progenitor for both long and ultra long gamma ray bursts. And first would rule out the tidal disruptions because we have clearly seeing different class of progenitors. But after that, magnetars and massive stars are still valid as progenitor. So just to go back to the physics, the magnetar basically provide the energy by extracting the rotational energy of a neutron star by magnetic brakes. So the duration of extraction is linked to the initial rotation speed for a given rate of emission. I'm not speaking about something that would emit at a lower rate. We are just assuming that we have the same kind of rate of emission. If you want to have something that lasts longer, you need to basically extract more energy and first have an initial rotation which is faster. And the problem is that for ultra long gamma ray bursts, the large energetics that we are seeing imply that the rotation speed is very close or even above the break limit for the cohesion of a neutron star. So we do see some equation of state of neutron star that would be able to handle that, but most of them would not be able to handle this. And in fact, as it has been explained into the previous talk, and I'm thinking into the next talks, magnetar are far more easier to use when you are dealing with short gamma ray bursts rather than with ultra long gamma ray bursts that basically are spanning 6 orders of magnitude in time more than the short one. The second option is to have the collapsar model. So basically the ultramassive stars is something that explains the long gamma ray bursts so far. And the total energy is linked to the size of the star. So you just scale up the star and you basically scale up the total energy. But because of the Eddington limit, you will not be able to increase a lot the accretion rates. So that means that still the emission rate of energy should be the same. So we just have to imagine that we have a larger star than the one producing normal long gamma ray burst, and we will have an ultra long gamma ray burst. Such stars are stereoized as population-free stars. So basically, we know that they should exist. It's easy to think that the collapsar model has a small advantage because you don't need to explain how to partly violate the law of nuclear and dynamical cohesions to produce an explanation for ultra-long gamma ray bursts like you would do with a magnetar. So if we assume that the progenitor is indeed an ultramassive star, then we have two options. The first one is that we are still sticking to the idea that we are dealing with something similar to population-free stars, so something which low metallicity. We know that population-free stars cannot be observed due to the reionization history of the universe. It's something that the universe was opaque at that time, so we cannot observe them. But this is the closest proxy that we can obtain. And it's very interesting to make observations, to test the stellar evolutions of these stars and all the models that we have for this star. We have also some kind of possible interest for light metal enrichment in the universe. We know that kilonova would produce heavy metals, and that's something which is interesting. But how you enrich also the universe into metals like carbon, oxygen, nitrogen, these kind of things, there a population-free stars would help you easily. Now, if we do relax the the non-metallic stars, we still have something which is interesting because we can still observe internal shock phase for a very long time. We also be able to study extreme physics, such as periinstability, for instance. And all of that is something that is very interesting for the understanding of physics as we have it. The problem is that we still imply that we need to detect ultra-long gamma ray bursts. And if at the moment with SWIFT we are covered, SWIFT is now close to the end of his life, and we need to think a little about the future. So the future at the end, when I prepared that talk and when I submitted, it was still 2 missions. Now is only 1 of them. So let's start by SVOM. Mission to be launched in 2022 if the COVID allow it. It's something that at start it was supposed to be launched now 2 years ago. It's a mission which is able to detect ultra-long gamma ray bursts up to moderate redshift. You have there basically the detection ratio of ultra-long gamma ray bursts as redshift, and you see that up to a redshift of 1 or 1.5, you should be able to observe a fair amount of ultra-long gamma ray bursts. And most of all, you should be able to classify these events as ultra-long gamma ray bursts in all these cases. Then, as I said, there was also the Tasers mission. So Tasers, unfortunately, has been denied flying for the M5, but all the work is done, and we only need a new slot at ESA. Let's call it the M6 slot. We just need to make some lobbying and to find somebody, I would say. It's a mission which is interesting because at the opposite of SVOM, the graph are not exactly the same. There you have a limit in red that give you basically the possibility to study ultra-long gamma ray bursts. So the possibility to have a spectrum that contain enough photons so that you have details into the study. And you see that at the end, up to redshift, I would say to 1.5, you can detect nearly all the ultra-long gamma ray bursts, but most of all, you can extract a spectrum which is meaningful. So this is interesting because at the end that gives you an information, but it's also because both missions design have taken into account the properties of ultra-long gamma ray bursts to enable these studies. And it's something which you need to take into account because at the end, observing long and ultra-long gamma ray bursts is not exactly the same. So that's my conclusions. Just to summarize, the ultra-long gamma ray burst is definitely a new class of events. And we consider that this is due to a third class of progenitor. We are now able to the physics at play inside this progenitor in the central engine. The technical details have mostly been cleared, but now we are really focusing to the stellar evolution, to the physics of shocks, and to the physics of very high fields. We are covered, I'm thinking, for the next decade, but we need to start lobbying for the next ones and remind all the time that ultra-long gamma ray bursts are not observed like long gamma ray bursts, neither like short gamma ray bursts, and that any mission dedicated to gamma ray bursts in general should also take into account these objects. Thank you.
Thank you, Bruce. Any questions for Bruce from the audience? Can unmute yourself and if you have any questions. Okay. I have a question on your, when you mentioned swarm and the sources. So the main reason is that they have more sensitivity or larger field of FOV, right?
Which one?
I mean, when you mentioned that we need future missions to detect more ultra long GRBs, we basically need a swarm. And the reason is that we need the more sensitive detector. I mean, if we define ultra long burst as gamma rays lasting for long, then why do you need a like a large field of view to detect them?
Okay, so it's just due to the fact that an ultra-long gamma ray burst lasts for so long that most of the instruments would consider that this is just an increase of the background.
Okay, so we need some like a yes, like around the threshold detections.
Yeah.
Okay.
Basically, the main of the work that have been done for SVOM was to tweak the detection algorithm so that it would not consider an ultra-long gamma ray burst as just an increase of the background, but really as an event.
I see. But currently you only have like less than 10 samples for ultra-long GRBs, right? But still like from 2005.
Yeah, it's still something which is very rare, yep.
Yeah, very rare. But on the other hand, you will define the stringent timescale as the duration of GRBs, and if you relax your definition from gamma ray to X-rays, I think probably we can define the X-ray flares as a stringent timescale. So in that, we probably have a large, much larger duration typical for GRB.
Yeah,
but
it's something the flares when we started to make this where I am.
You change everything. So I mean, then a lot of long GRB become ultra long.
Yeah. Basically, it's something that was difficult to for us when we basically had to consider the flares that are here, because technically this is a restart of the central engine. So where do you put the start back and the stop again? It was something, but it's something that we discussed a lot with Julia to understand if pushing flares would basically do something, because then obviously nearly all the bursts become ultra long just because the central engine reactivate.
Yeah, I agree.
And at the end, we decided that it was better just to consider, okay, let's assume that we are just looking for the first initial switch on and off of the central engine. And that after that, it's what is relaying around.
Okay.
But I totally do agree with you that you have some giant flares that you have seen in X-ray that technically, if you put that into the light curves, yes, that won't become an ultra long.
Yeah, so we have to define the gamma ray burst in such a way that we have to use the energy range. So it is a gamma ray, then you with gamma ray. Yeah, I agree with that. Okay, thank you, Bruce. We should go to next talk from Thomas, and we'll be talking. Thomas, are you here? Yeah, and Thomas will going to give us talk on the discovery and the confirmation of the shortest gamma ray burst from the collapsar. Go ahead.
Awesome. Thanks for the introduction. So, hello everyone. I am Tomas Ahumada. I'm a graduate student at the University of Maryland in College Park in the US. And I'm here to present you the discovery and confirmation of the shortest gamma ray burst from collapsar. Here also on behalf of many people, as you can see here. This work was submitted and accepted into Nature Astronomy. You can check it out on this archive URL. So this is just the outline of the talk I'm going to give today. I'll start with a little bit of the background so we're all on the same page regarding the subject. I'll talk also about the CTF strategy because I don't think most of you are familiar with it. Then we'll dive into the shortest collapsar GRB 200826A. This is the light curve on the Fermi light curve, and I'll finish with some conclusions. And to provide some context, I am currently leading the Zwicky Transient Facility efforts for finding the optical counterpart of short gamma ray burst. So this effort, highly motivated by the joint discovery of gravitational waves and short gamma ray burst coming from a binary neutron star merger in 2017, that led to the discovery of the optical counterpart of this gravitational wave 17017. Just mentioning that the GRB that was detected as at the same time, 17017A, was not different from the bulk of the short GRB population, besides being part of the low luminosity population. But this object, the uniqueness of the object that we're going to talk about today, GRB 200826A, is that even though we're aiming to trigger on short GRBs that come from compact binary mergers, the GRB population seems to overlap, and there's no certainty on whether we're going to find an afterglow, a kilonova, or a supernova. The traditional separation is set to 2 seconds. However, there are a few examples that challenge this classification between short and long GRBs. So on one end, we have GRB 090426. This was a short GRB at a very high redshift in a blue luminous star-forming galaxy. That in this case, no supernova was observed. However, several authors suggested that it was linked to the death of a massive star collapser. On the other end, we have GRB 060614. This was a long GRB, longer than 100 seconds, found in a galaxy at a redshift of 0.1. And due to its proximity, you would expect a bright supernova, but observations with the Hubble Space Telescope did not show that bright supernova that is expected from those long GRBs. So the community was puzzled because also the energetics of this GRB were aligned with the Amati relationship for long GRBs. And I'm just showing this to an example of cases that challenge the traditional classification of short and long GRBs. For the purpose of this project, we are using the Fermi satellite and hunting for short GRBs, mainly because, and we're using GBM, mainly because it has a wide field of view. It detected 17017, that's what the things we're looking for. It is sensitive to higher energies than Swift, and it also detects GRBs at 4 times the rate, short GRBs at 4 times the rate of Swift. The biggest challenge is that GBM produces very large localizations. And that's why we're using the Zwicky Transient Facility. So the Zwicky Transient Facility, CTF, it's camera mounted in the 48 inches telescope in Palomar Observatory. And here I'm showing the footprint of CTF compared to other wide field of view instruments. The 47 square degree stands out, and has allowed us to overcome this problem of having large localizations coming from GBM. CTF was designed to reach 20.5 magnitudes in depth in 3 different filters, and it scans the sky every 3 nights. As again, you might not be familiarized with CTF, this is how we look for these transients. So this is a screenshot of Fritz, the platform we use to interact with the data. You see here the light curve of particularly this one, CTF 20 of whiskey. You have the positions and the cutouts. So how does this work? CTF takes an image every night of a given field, subtracts a reference image, and then you can see what is left in a given subtraction. You can also compare to other catalogs and see what's behind we have implemented a target of opportunity strategy that includes the tiling of the regions. Here you can see the black squares tiling the huge region of this particular GRB. The strategy also includes the scanning and vetting of the candidates. We use the filtering scheme that you see here in the chart flow. We look into the previous history, the light curve, the color, the magnitude evolution. We check for AGNs and slow-moving objects to finally reduce usually the number of candidates to less than 1% of the original number of alerts. Then we visually select the most interesting ones and assign them for follow-up. We move from CTF to other telescope with dedicated time to follow up these sources. We prioritize spectroscopy, but usually we only have access to imaging, and we're looking for fast fading transients. So you can see here in red the kilonova models that show a very fast decay, but also the short GRB afterglows that also show a very fast decay. And there's our object here in blue. Again, the first 2 points were taken with CTF, but then CTF is not powerful enough to follow it up, so we have to use other facilities. Finally, with all this in mind, I'm going to present you the case of GRB 2008-26A. So here in blue, you have the 90% credible region of GBM. In gray, you have the CTF tiling. So we took a bunch of images of this region and then circulated the candidates found in this region. Those are the ones in green. Thanks to IPN, the region was reduced to a few arc-minute squares, and XRT was able to tile, then observe and circulate the X-ray sources in this region. And only one of them had an optical counterpart from CTF, but also was inside the IPN, which is this one here. CTF 20F Whiskey was discovered 0.2 days after the trigger. You can see here the first image. This is the reference image. It's really something that was not there. In the legacy survey, you can see a very faint galaxy over there. That is the host, actually. The interesting thing about this GRB is that it lasted 1.1 seconds, and it was first cataloged as a short GRB because of its duration. However, since once the redshift was available, the EconomsWind team pointed out that the energetics of this GRB were aligned more with the long GRB population. It was actually within 1 sigma of the Amati relationship or their burst. And if you look in the left plot, you have the e-peak duration plot from Fermi. This is color coded by the probability of being a short GRB, and our particular GRB has a probability of being part of the short GRB population of 74%. So we have a dilemma. Fermi GBM says that it's a short GRB with the 74% probability, but EconomsWind says that it falls outside the short GRB population. It's potentially a collapser. So we need to use different methods. We went and modeled the afterglow. We studied the galaxy and went for a supernova hand. And just as in spoiler alert, we have evidence that supports that it's a collapser. I'm just gonna first refer to the afterglow. We use Afterglow Pi to model the Afterglow emission. This uses MCMC to derive quantities like the isotropic kinetic energy and the circumburst density. And having those, we can compare them to the wider GRB population. So I'll put here on the top row the short GRB populations, and then on the bottom the long GRB. The first column shows the density. So you can see here that the density of our GRB aligns with the short GRB population. It's pretty much in the middle. However, it's farther than 1 sigma from the mean of the long GRB population. That is not alarming because there are other examples of long GRBs that have extremely low densities, such as 160625b, for example. And when looking into the energetics, the short GRB population, it's usually less energetic. Our particular GRB stands out as being very energetic in this population. However, if you put it in the long GRB population, it's within 1 sigma of the mean. So the analysis of the afterglow alone does not allow us to solve this mystery just yet. So what about the galaxy? The host galaxy study, to study it, we took a spectrum and also modeled the photometry using perspector. The redshift of this galaxy was 0.74, has a strong O2 and O3 features, and we calculated the offset of 2.5 kiloparsecs from the center of the galaxy. We then compared to the bulk of the populations. So here you have two histograms showing the cumulative probability of finding one of these GRBs and what's the offset at which you will find it. Again, it's not very conclusive. This particular GRB is consistent with being both a short GRB or a long GRB. If you look into the mass of the galaxy that we derive from the models, either Prospector or PPXF, we derive around 10 to the 10 solar masses. And again, not conclusive. Both populations overlap, and it's not, particularly peculiar. So from the galaxy perspective, again, it's not conclusive. The last resource we had is to go and hunt for a supernova. So we were awarded time at the Gemini Observatory through DDT. We used it to observe the source 3 nights and 3 epochs. We used image subtraction and discovered an excess on the I band that couldn't be explained by the afterglow. So on the left, you have the models as shaded regions. The colors represent different bands. But what I wanted to show here is that our I-band point here does not fit correctly the afterglow models. So since the afterglow models couldn't really explain the GMOS I-band access, we additionally modeled the afterglow plus a supernova component. So for this, we used 1998 BW as a template, and we scaled and varied the stretch and scale. This model fits the GMOS data point much better. It's within 1 sigma. So here you have the posterior probability of just the afterglow, the blue one here. The yellow is the afterglow plus the supernova, and the detection we have is here on the black dotted line. So you see here that the detection we have aligns, and it's fitted by the afterglow plus supernova model, but not just the afterglow. This makes GRB's 2008, 26A consistent with being a supernova, and hence coming from a collapsar origin. This would make it the shortest collapsar ever found. And this is very interesting and exciting because it shows that there are extreme objects waiting out there to just be found. As part of our conclusions, I just wanted to remind you that the duration of a GRB depends on the time that the engine is active, but also the time that it takes it to break out through the envelope. And particularly, our GRB here, this one here, was long enough just to break through the envelope, and it sits in the brink of being successful and a failed GRB. With the local rates of long GRBs and supernovas, 1C broadline, we can now say that this is an example that lends credibility to the claim that most collapsars fail to produce ultra-relativistic jets. And finally, this is my last slide. I just wanted to highlight that we've used CTF effectively to follow up these larger regions. We've used extensively the data from other spacecraft, and that has helped us a lot. The deep follow-up of these unusual GRBs can prove the nature of different progenitors. I guess we're gonna hear more in the next talk. And the discovery of this GRB 20826A and its associated supernova suggests that the majority of the collapsers fail to produce these ultra-relativistic jets. And with that, I guess I'm gonna just thank you all and take questions.
Okay, thank you, Thomas. Any questions? Any questions? Okay. I have a question. Do you have any other further follow-ups on the supernova?
We did take a few other images, but we didn't detect anything. So I guess it was.
When you look at your model, the line supernova bump, probably, yeah, it's too late now, but last year, maybe in the end of last year, we still.
I think that we have at least 3 images. We could take another one to use it as a reference, but I think that we catch the supernova at the very end, so it was probably too dim. It was very far as well, so it was pretty challenging.
So effectively, there's only one data points for the supernova. Others upper limit. Yeah.
And then upper limits, yes.
Yeah. Yeah. Okay. If there's no other questions, let's thank Thomas again. Let's go to another next talk by Zike, and he'll be talking about the same GRB. Okay. Okay, go ahead.
Okay, hi everyone, and I'm a graduate from the Nigerian University, and as a master graduate in BIMIN's group. And in this session, I'm going to show our recent work about new troublemaker gamma bursts occurring on 26th August 2020, which may be a new type of GRB. One is a true short, but all the other properties in our analysis point to a massive star region. And thanks again to Thomas' talk about his richful introduction, and something very richful information about its localization and some afterglow data introduced. So, okay, let's move to the content of my slides. Okay, when talking about the particular sort of this GRB, we may as well go quickly back through the traditional GRB picture. We have achieved a basic common on GRB classification since the 1993, which can be concluded that short versus long and the soft versus hard since from the Betz era. We've known the duration is detector dependent. So in spite of its unreliability, 2 seconds is still a wide accepted criteria in the GRB community. Meanwhile, there are still some mysterious GRBs don't belong any of the 2 camps, like the ones with intermediate duration and some ultra long GRBs also were talked in very detail in the Bruce talk, and how to decide these ones where we are maybe need further researches of them. But no matter how strange a GRB is, it can never be intrinsically long as a physically short one, but with an apparently long duration, and vice versa. At least we believe so. Just like the gamma burst found in 2006, it seems naturally long but physically short. What means the naturally is what the experience we observed is, right? And the total observed one is found in 3 years later, 090426, which is an apparently short but physically long one. And the fighting between short versus long had begun from the 2006. So the typical short ones may include those combined with the short spikes and the long tails, just like the cat in the lower left, and like the GRBs, the representing one is the GRB 060614, and the typical long ones could just show their tip of iceberg, like the most representing one is in 2009, and the arguments between the short versus long scheme and other parties have never been stopped since from the beginning of the research of GRB. Okay, with more data in the afterglow epoch, properties of GRB's host have been found. Instead of short versus long scheme, we tend to classify GRB physically into 2006, that is type 1 versus type 2 scheme, and this scheme have been gradually accepted by us, just mentioned in the 2006 Nature paper of Professor Zhang Bing, and according to previously mentioned software GRBs, we thought we revealed the mysterious masks of them and know how to make a physically long one short and a physically short one long. That is to say, to observe a short GRB with very sensitive detectors, so we can say its lower energy tails last several tenths of seconds. And so if we ignore the extended emission tail, we can make a short one from the long GRB. And on the other side, if we put the long GRB at a large distance, we can only see the peak of the whole burst, just like a fat tip of the iceberg. And as mentioned before, a physically long GRB can never be truly short. We can also say a physically long GRB may be apparently short, but cannot be intrinsically short. In the hyper-accreting black hole central engine scenario, the duration of the central engine activity should be at least the freefall time scale of the star. So the typical massive star core density is 100 gram per cubic centimeter, and it will lead to several hundreds of seconds of the duration. And there are also some attempts to reduce this value. The minimum one is 10 or 20 seconds, which can only be achieved by some successful numerical simulations, but it can never be 1 or 2 seconds. That seems unchangeable and perfect story. But until last year, a troublemaker, 208268, emerged. That's like a real troublemaker to broke our recognition of the current GRB picture. Okay, now we need to move back to the previously mentioned true short of the GRB. The first of properties is the appearance of this GRB is light curve, shows a true short. For proving the short of 208268, some other things maybe need to replenish, just like the spectral lags, and means the time delay of the photons from the different energy channels, and the F parameter representing the ratio between the peak flux and the background of the GRBs. So what would happen if we put this naughty guy into the distribution of the left green highlight parameters of the whole GRB population? We can see that the short duration with a high signal to noise ratio shows its high brightness, relatively low hardness ratio, and the high F parameter. All these things let us regard it as a no doubt short one, at least not because of the tip of iceberg effect. Okay, until now, These things could be ended up with an usually short GRB story, but you never know when we were about to go smoothly all over the properties of the 208-6A, such as its spectral lag, a relatively big value, which behaviors weirdly relative to a typical short GRB. And what's more intriguing is its other physical nature. Okay, let's move to the next stop. Let's move to next step. That is spectral analysis. Spectral analysis also gives our crucial clues, like the peak energy and the spectral evolution and any other spectral features. 208-6A exhibits not too much deviations from the short GRB population, except a little bit high isotropic energy. When put this isotropic energy and the peak energy together, like the Amati region shows, which exhibits the different tracks of short and long GRBs. Another energy-related parameter, epsilon, was proposed in 2010 and can distinguish typical short and long GRBs very well. All these correlations shows the same string as the spectral lag. Both of two above correlations of 208-6A categorize it as a typical long GRB. So that's the same string. That's very string to and be offset to the true short of the lecture of the 208-6A. And we use the following optical data from the GTC telescope. We can see it's close to the host center with a offset of 2.6 and a relatively large star formation rate and the star formation rate and the specific star formation rate. All the distribution of these properties show it shall belong to the type 2 group. Okay, the last and the convincing evidence is this short GRB originated in collapse scenario. It shall be supernova associated, and what's the luckiest is it did emerge an optical excess in the band detected by Gemini multiple object spectrum. Also be talked in the Thomas talk. And the supernova involved afterglow model gave a good fit as well. All this further firmly prove its massive star origin, which is to say it should be a type 2 GRB. Okay, and how to produce this kind of weird GRB? If it's really originated from the massive star collapse, how to produce this GRB less than 2 seconds? Here we consider several ways to get around this. If you believe it's really a short duration GRB, but all of the aspects are consistent with type 2 GRB, we need to go back and again see the freefall time scale of the stars. If the time scale is around 1 second, then around 1 second, density should be far beyond our knowledge of the massive star progenitor. So, we consider it could be a wide dwarf involved system. Maybe a wide dwarf neutron star binary system could work when a massive star or wide dwarf is close to the tidal radius of neutron star. The neutron star will disrupt the wide dwarf and form a Thorn-Zecco-like object with a disk. The accretion time scale of the disk is around 1 second, which is consistent with the short duration feature. In fact, In fact, we also do an, I don't know why this slide is short, it's stopped in this slide. Okay, sorry. In fact, we also do an extended research of 20826A for doing a test for of this GRB being a neutron star plus white dwarf system as the origin of 20826A, and the Magnetar as the remnant. We can see from the fate that the fitting results further solidify our speculation, and we never consider this kind of event rates in our near universe. It seems a feasible way to produce such a weird jerk. In addition to previous one, 20826A could possibly be born in supernova scenario, where supernova happens before the jet launch. So the left stripped compact neutron star could accrete and implode to a black hole, then launch a short duration jet because it's in a very young, clean environment. But you cannot well explain the late energy injection shown in the X-ray afterglow data. Alternatively, the short GRB maybe not powered by the accretion at all, like long GRB is supported by differential rotation of neutron star. If we increase the seed magnetic field strength to 10 to 14, a short duration may be achieved. It's bad of the challenge for such a big magnitude of the magnetic field. Or maybe the central engine of the GRB certainly acts in long time, in which the new magnet of the merger remnant injects the baryon loaded neutrino-driven wind to make the jet mildly relativistic, or even non-relativistic. So that the no bright gamma rays could be produced during most of the central engine time, so that only a few parts of the GRB could be observed as. Another long duration central engine case is the massive star collapse GRB. Massive star collapse. The time of the central engine is long, but most of the time is consumed to go through the stellar envelope. Also be talked in the Thomas be mentioned in the Thomas talk. So we can only see a few part of the 20826A, just things like the previous case. That means the GRB, but we need to. That means we need to introduce coincidence between the time scale of central engine and the jet. So both of the two channels means the GRB is not strong enough with a dirty engine. So in this situation, this GRB should not be as the same bright as we observed. But all these assumptions is not studied with the detailed data of this case. So maybe the future numerical simulations could help us solve them. I hope that the story seems could be ended up, but when we see the whole story, whole GRB history, there are still some puzzles we need to address. Plus the previous confirmed first gamma burst from the Magnetar giant flares in the talk of June, and the 20826A. They are all just the beginning of the exploration of the type 3 and maybe the type 3 of the type 4 gamma burst. And the recent hot faster radio burst may be revealed its association with the GRB. Okay. Okay, that's the slide I'm talking. I'm just talk about this possible cans of GRB. Okay, all in all, we still have a long way to go in this journey towards the GRB field, and thanks this.
Okay, thank you, Zico. Any questions for Zico? Please, Royal, go ahead.
Maybe I missed your point, but in your model, white dwarf, neutron star merger, what makes the observed supernova-like bump?
You mean the the merger model, right? White dwarf neutron star merger model.
Yes.
Yeah, it's difficult. It is difficult. We have to assume here.
You show some figures.
Yeah, but we have to assume, there's only one data points from the supernova. It's very challenging. We have to figure out.
But in your talk, you showed the
fitting, right?
model light curve in the context of white dwarf neutron star merger.
Yeah.
Yes, that figure. So what is the dashed line?
The dashed line is actually we assume there is a bump. It's difficult. I agree with you, but we do assume in this model that there are some interactions between the ejector, in this case, ejector and the medium, ejector medium. So there may be a bump, but this model will produce two bumps. One is this one, the right one in the early time, then late time there's an additional bump.
Optical flare for the merger nova and
optical flare for the merger nova, so-called merger nova. There's a neutron star, plus a white dwarf, then produce another neutron star with a lot of ejectors. But
okay, thank you.
Yeah. Okay, Thomas, please.
I was wondering, would it, in the same topic, would we have would you see something in the infrared as well? Kind of like a kilonova thing? Because of
I think our author, the first author, is here, right? Zhongkai, do you want to answer this question? I mean, infrared modeling. Zhongkai, are we here?
Or would it produce, our process nucleus indices? Would you expect?
Yeah, that would be interesting. So we have this 3 band. So in principle, we should be able to calculate the infrared. Yeah.
Because I think there's another paper on the archive that was submitted to APJ that has an H band detection. So we have an I band and an H band. So maybe you can.
Yeah. Thank you for the comments. Okay. Any other questions from the audience? Let's go ahead with the next talk by Royal. Can you share a screen? And Royal will talk about a possible link between the normal long GRBs and this particular GRB 2826A. Please.
Can you hear me?
Now we can, yes.
Okay. Okay. Hello, I'm Ryo Yamazaki. I'd like to thank session organizer Bin for giving me this nice opportunity to introduce a model linking between the recently observed short collapsar event 2008-26 and the normal long GRBs. So this event was very interesting for us. This is observed light curve. The duration is about 1 second. And the in the EPIC EISO plane, this event sits in the typical range for long GRBs, not in the short GRB range. And the possible bump, supernova bump, was observed. And the host galaxy is star forming. And so in this talk, I'd like to tell you why this event is interesting for me. So in order to do that, so let's going back to long before from now, that is pre-Swift era. These are typical light curves of short GRB and long GRB. And typical long GRBs consist of a lot of short spike, short pulses like this. And the duration distribution is given by Batzi in 1990 somewhat. And clearly the distribution was bimodal like this. And the event rate of the shorter side is 300 per year. And the longer side, the event rate is 1,000 per year. And just before the launch of the Swift satellite, thanks to Heti-2 satellite, the people confirmed the long GRBs is a massive star progenitor in origin. So that is collapsers, which is the collapsing, rotating massive stars. But we didn't know the origin of short GRBs. So origin of short GRB is still now uncertain, but most plausible is the CBC, compact binary coalescence. Another possibility is a giant flare of nearby soft gamma repeater, but the contribution to the whole population may be small. Finally, the third one is collapse of a massive star, collapsers, that is same as long GRBs. So just before the Swift era, we proposed a unified model of gamma ray bursts. The motivation was like this. GRBs are observationally categorized into various subgroups, like short and long GRBs, XL-rich GRBs, and so on. And however, event rates of short and long GRBs are similar, and some of their observed quantities are similar. So motivated by these observational facts, we constructed a possible unified model of short and long GRBs, XL-rich GRBs, and XL flashes, like a unified scenario of active galactic nuclei like this. So this was a basic schematic picture of a unified model. Let's consider the central engine launches some structured jets like this. If we see this jet in this direction, for example, we observe the jet emission as long GRBs, but if we see this jet in another direction like this, we observe short GRBs and so on. So we adapted inhomogeneous jet model, so-called patchy shell model or mini jets model. A relativistic jet consists of many patchy emission regions, or a lot of mini jets like this are randomly launched by the central engine. So this figure shows the emitting region viewed from the central axis of the whole jet. So this is a whole jet. The whole jet consists of many emitting regions like this. And emitting regions are yellow colored regions. Okay, this is a model setup. One of the motivation to consider such patchy inhomogeneous jet model was the collapsar simulation given by Jean et al. And a lot of authors so far. Jet may become inhomogeneous during propagation into progenitor star due to many hydrodynamical instabilities and so on. So anyway, we gave one example in Yamazaki et al. We considered jet structure like this. So the small patches are emitting regions. So at the central part, there are a lot of emitting regions. If we see this jet from the central axis, I mean the observers is in the line of sight A, direction A. We simulated the observed light curve like this. So this is a long GRB. On the other hand, if we see this jet in direction C, then only one emitting region was seen. So this is short GRB. So the other emitting region situated here do not contribute to the observed flux because of the relativistic beaming effect. Subsequently, we showed that our model could explain the observed bimodal distribution of the burst duration. Again, if we set the jet structure like this, we get a T90 duration distribution like this. The physical reason of bimodality was clear. There are two independent time scales. One is the duration of a single pulse emission, which makes this peak. And the other time scale is the duration of the active time of the central engine, which makes this peak. So physically, the bimodality is very clear in a unified model. So, but we had many trials for different jet structures. If we set these jet structure, we get this T90 duration distribution. And if we set this distribution of emitting region, we get this duration distribution. So the number of observable short GRB is very sensitive to the angular distribution of emitting regions. This fact was soon pointed out by another group, Janiuk et al. They followed our models and showed that shorter side peak height strongly depends on model parameters like this. So what is the afterglow predicted by our unified model? So our model looks somewhat complicated, but it is not so complicated. The inner region of the whole jet, inside the dashed line, inner side of the whole jet can be filled with kinetic energy, but it is not internally dissipated. So here and there, the white region, not the yellow region, were filled with kinetic energy and do not produce prompt GRB emission. Even if the kinetic energy is absent, like mini-jets model, the sideway expansion occurs and the energy redistribution effect makes a smooth energy distribution like this. So we expect afterglows may be similar to those of structured jets. And I would like to point out this event. This event was reported by GCM with duration 0.6 seconds. And E-peak and E-ISO are consistent with the amortization in the amortization for the long GRB, and it showed a possible supernova bump and the host is star forming. Oh, so this is clearly the short collapsar event, I thought. But soon after the publication of these papers, the Arimoto et al. Showed that T90 duration distribution is longer than 2 seconds. So next, eventually the Swift satellite was launched, and just a few months later, after the launch of the Swift satellite, several short GRBs were successively detected and localized. And some short GRBs occurred in elliptical galaxies. This was very remarkable because all long GRBs occurred in star-forming galaxies. Elliptical galaxies have all the stellar population, so CBC, compact binary coalescence, neutron star mergers became the most plausible candidate for short GRBs. And subsequently, possible kilonova detection from a short GRB was reported. This is a famous event. So soon after the Swift error, it is believed that short GRB is CBC in origin. However, the situation became somewhat complicated. Some short GRBs were long. I mean, if we see the light curve in the gamma ray band, the event is short. But if we see X-ray light curve, there are temporary extended emission like this. So this event is long or short, I don't know. But such events made a challenge for CBC models. And on the other hand, there are also unusual events in long GRBs. This event occurred. This event had the duration of 100 seconds and occurred very nearby. The observed light curve is black points shown like this. And if the burst was so nearby, we would see the supernova bump like this, but we didn't see them. So this is not a collapsar event, but CBC, people believe. So the GRB people are confused, and the situation became very complicated. Now, the burst duration alone is not a good indicator of the origin of the GRB. I don't explain details of this diagram since it is very complicated, but we should take into account various observed facts is needed to judge if each event is CBC or collapsar in origin. One of the easy way to disentangle CBC and collapsar is the EP and E-isoplane, I think. And after the launch of the Swift, after 2005 or 2006, the Swift detection rate of short GRBs became smaller for me. The contribution of CBC, which means the well-localized Swift short GRBs, is small. There may be a lot of short GRBs which are missed by Swift BAT. So this is a BATSI duration distribution. And this is a duration distribution given by Swift BAT. So they are CBCs in origin, I agree. But we still don't know the origin of these guys. So I hope a revival of our unified model of long and short GRBs. People believe it's like that, and but we expect it like this. So the collapsars makes bimodal distribution, and CBC burst is smaller than collapsar events in the T90 duration distribution. And now we detected 2008 to 26A. So that's why I'm interested in this event. So in summary, more short collapsar events are desired. We hope this event is not unusual. So please do not say this is a troublemaker. So that's all. Thank you.
Thank you, Raul. Any questions?
I have a question.
Oh, okay, go ahead.
Well, actually, you once said maybe I missed it, the inner region do not dissipate internally. Do you mean it won't be internal shock or something?
Right. So yellow region produce the prompt emission, and but in the white region, even if there is a outflow, but this region do not produce the internal shock.
Okay. Thanks. Asaf, please go ahead.
Thank you for the talk. Maybe I missed that part, but what would be the physical reason for producing these mini jets and that you're anticipating?
I mean, so for example, along with the collapsar models, the jet is propagating into the progenitor star, and there are many hydrodynamical instabilities like Kelvin-Helmholtz instabilities and so on. And then the jet became naturally inhomogeneous.
Yeah, but there is still some inhomogeneity. You're right, but I think that for what you're proposing, right, you require a big difference between the emitting regions in terms of velocity.
Right.
Is it something that you're actually seeing in simulations, or is it something which you see? I think what you need is a bit more than that.
Yes, so the important point is that we only consider the emitting region, so which is internal shock region.
Okay.
Okay. Thomas, can you go ahead with your question?
On the last slide that you showed, do you have any ideas on what are the rates / ratios between the sorry, so yeah, like what would be the ratio that you would expect from, you know, having missed collapsers?
Sorry, one more again.
In this, like, in this plot on the short GRB side, you have the missed collapsers and then the CVCs.
Yes.
Do you have any idea on what your model would predict in terms of what are the ratios? Is it like, you know, 80% missed collapsers and then 20% CVCs, or
So as we write in this part, the peak height of the shorter side of the duration distribution is very sensitive to the jet structure. So so if the observers fix the value, we adjust the model parameters to reproduce the observed event rate.
I see.
Yeah, so I showed this slide. So the peak height is very sensitive to the jet structure.
I see.
Yeah.
Thank you.
Okay. Okay. Thank you, Thomas. Any other questions? Okay, I think you mentioned, I have one comment. So I think you mentioned 040924. For that GRB, it is short, but the tip of iceberg effect is, I think, compared to this one, is not so, it cannot be ruled out, right? You compare the peak versus the background is only 3. But compared with 2008 to 26A, the so-called F parameter, which is peak divided by background, is 8. So definitely we don't have tip of iceberg for 2008 26A, but we probably have a tip of iceberg for this burst, which suppose that maybe we just observe the tip as still a long GRBs. So in that sense, still 2008 26A is very special in its shape. It's very sharp. So that's compare with the previous one. So
thank you. That's the difference between this event and the recent event. Okay, thank you.
Yeah, yeah. Okay, thanks again, Roy, for your talk. So let's go to the next one. I hope I pronounced correctly. Yuri Sato, for your talk on GRB 190826A. So go ahead, please.
Hello, I am Yuri Sato, a graduate student at Aoyama Gakuin University, Japan. I will talk on off-axis jet scenario for early afterglow emission of low luminosity gamma ray burst GRB 190829A. This presentation is the content of this paper. This is summary. We have investigated an off-axis jet scenario in which we have invoked a two-component jet model to explain observational result of 0829. So some low luminosity GRBs may be explained by off-axis jet scenario. Gamma ray bursts are the intense bursts of high energy between 10 keV and 10 MeV photon. The duration of prompt emission ranges between 0.1 and 1000 seconds. After prompt emission, multi-wavelength afterglow lasts for a long time. Some GRB have small isotopic gamma ray energy and luminosity. This is low luminosity GRB. Low luminosity GRB may be explained by off-axis jet scenario or shock breakout and so on. However, the origin is unknown. GRB 0829 is classified as low luminosity GRB. This event has unusual features. First, it is detected by heads with 20 sigma at about 20,000 seconds. Second, it occurs so nearby with low redshift. Third, prompt emission has small isotopic gamma ray energy and peak energy. Fourth, early X-ray and optical infrared afterglow short rising path and has achromatic peaks at about 2000 seconds. We consider off-axis state scenario to explain those unusual observed properties. Next, I will talk on the observational result of prompt emission. The left-hand panel shows light curves of prompt emission. The prompt emission consists of two temporally separated components. The observed value of isotopic gamma ray energy and peak energy of episode 2 are consistent with Amati relation, while those of episode 1 are in the region of low luminosity GRBs. Both episode 1 and 2 have small isotopic energy and peak energy than typical long GRBs and the other very high energy gamma ray events. Next, I will talk on the observational result of afterglow. The left-hand panel shows light curves of X-ray afterglow of TeV events. The other very high energy event showed monotonically decaying X-ray afterglow emission. However, only 0829 shows rising path. The right-hand panel shows multi-wave lengths of light curves. Early X-ray and optical infrared afterglow emission showed a rising path and had achromatic peaks at about 2000 seconds. There are various theoretical models to explain bumps at 2000 seconds, like X-ray flare, baryon loaded outflow, positron-electron dust shell, reverse shock, and our off-axis afterglow. Next, I will talk on off-axis jet scenario. If the jet is viewed off-axis, the relativistic beaming effect causes the prompt emission to be dimmer and softer than on-axis viewing case. The bulk loading factor of the jet is initially so high, thus the afterglow emission is very dim because of the relativistic effect. As the jet recedes, the beaming effect becomes weak, resulting in the emergence of a rising path in afterglow light curve. After the peak of the emission, the jet has smaller loading factors, so that the light curves only weakly depend on the viewing angle. Next, I will talk on model description of jetted afterglow. A relativistic jet interacts with ISM, forming external shock, radiating synchrotron emission in X-ray, optical, and radio bands by accelerated electrons. We determine model parameters to explain multi-wave length afterglow. Next, I will talk on off-axis afterglow emission from a narrow jet. The initial opening half angle is small, so that I defer to narrow jet. The straight line shows the result for our parameters. Our off-axis afterglow model will explain the observational result of early X-ray and optical afterglow. For comparison, the dashed line shows the light curves in the on-axis viewing case, in which the X-ray flux peaks much earlier than optical one. However, it is hard for a single jet to describe the emission from all wavelengths at any time. Next, I will add another component to enhance the rate X-ray and radio fluxes. We consider a two-component jet model in which another wide jet is introduced addition to the narrow jet. The solid line shows the superposition of each jet emission component. The parameters of the narrow jet are the same. This is wide jet parameters. One can find that the early achromatic peaks in X-ray and optical band are explained by the off-axis narrow jet emission, and that the late X-ray and radio afterglow are interpreted with the wide jet emission. The optical observation is brighter than our result, later than 50,000 seconds. It is supernova component. Next, we discuss whether isotopic gamma ray energy and peak energy from our narrow jet were typical or not if it has been viewed on axis. If the narrow jet emitted episode 1 and 2 of observed prompt emission, on-axis quantity are similar to typical long GRBs. If the narrow jet cause episode 1, then the estimated prompt emission efficiency is almost typical. However, on-axis peak energy is located at the highest end of distribution for long GRB. On the other hand, if the narrow jet produces episode 2, then on-axis peak energy is smaller, though prompt emission efficiency is somewhat higher. It is uncertain whether the narrow jet caused both episode 1 and 2. Finally, we estimated the very high energy gamma ray flux at 20,000 seconds, assuming SSC flux in the Thomson limit. We have found that the narrow jet dominates the observed gamma ray emission at 20,000 seconds. On the other hand, the very high energy flux from the wide jet has brightened until 50,000 seconds. After this time, the flux decayed. The right-hand panel shows VLBI radio source. The observational results show full width half maximum. On the other hand, our wide jet shows minimal value of radius over loading factor or radius time jet opening half angle. Our model parameters determined by X-ray, optical, and radio afterglow may largely explain observed TeV flux and radio size. This is conclusion. We have investigated an off-axis jet scenario in which we have invoked a two-component jet model to explain observational results of 90 August 29th. According to our model, the early X-ray and optical afterglow could be off-axis emission from the narrow jet, and the late X-ray and radio afterglow came from the wide jet. Our parameter may also explain very high energy flux at 20,000 seconds and radio side observation. So some low luminosity GRBs may be explained by off-axis jet scenario. That's all. Thank you.
Thank you, Yuri. Any questions? Any questions from the audience? Okay, I have a question. Can you explain both the decay of the high energy TeV emission and also the spectral slope of the high energy emissions? I mean, in this model.
Excuse me.
I mean, this is when you look at the TeV emission, it has a slope, right? You have two components making one single polar decay slope, narrow and wide. Okay, it doesn't fit the data well to me. I don't know. Just comments.
Can I answer the question?
Yeah. Okay. Sure.
Yeah. So the first and second point at 20,000 seconds are well explained, but as you said, the later points are difficult to be explained.
Maybe. And regarding the radiation mechanism, do you think they are still a inverse Compton or a singletron from your modeling, or any other hints?
The SSC.
SSC. Yeah. Okay. 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 Any other questions? If not, I think that's the end of this section. So thank you again for everyone to come to this session. And so see you in the future. Bye-bye. And good night, good afternoon, and good morning, everyone. Bye.
Thank you very much, Bin Bin.
Thank you for coming. Bye.